let's talk about capacitors.
Ow! Woo!
There is energy all around us. The energy is both yin and yang, positive energy and negative energy. Only a select few firebenders can separate these energies. This creates an imbalance. The energy wants to restore balance, and in the moment the positive and negative energy come crashing back together. You provide release and guidance, creating lightning.
I'm ready to try it.
And just like always, wise words from Uncle Iroh.
So, what is a capacitor? Well, a capacitor is a device using electricity that is used to store electrical charge and energy to use for later. And we use them all the time. Think about like your touch pad on your phone. Basically, when you touch the screen and it changes to something else, that's just a capacitor turning on and off. And the information is being given off by stored charges. So there's charges stored in one area, you touch the screen, and then it allows those charges to get discharged to a different area, which changes what you see on the screen. So capacitors are used all the time. Now the symbol for a capacitor is very similar to a battery, except it's two parallel lines that are equal sizes, where a battery is one long side, one short side. There are a couple of equations I'll talk about in a second here, but you can think about, here's one way to use a capacitor. Let's say you had a battery here, and a capacitor, and a resistor, and a switch, right? So we know that the positive side of the battery is like right there, negative side of the battery is right here. So if this switch is open, electricity is going to flow out of the battery, and it's going to go, it can't go this way because the switch is open. It's going to fill up that side of the capacitor. So this side of the capacitor, I'll go over here, is going to fill with positive charges. And those positive charges are going to repel the positive charges of this one, and make this negatively charged, and that current is going to continue going this way. But the current is actually going to essentially stop. It's just that it wants to continue that way. So essentially you made a circuit that's kind of like temporarily paused. It's like the circuit is running, but it's paused once the capacitor is charged up. It's almost like a charger, essentially.
Alright, let's test this out. So let's say I have a battery hooked up to a capacitor, and right now electricity cannot get to this light bulb here. There's no possible path for electricity to take to that light bulb. So now that voltage is on the capacitor, this top side is positively charged, this bottom side is negatively charged. So all I have to do is flip over the switch. But as I do that, let's pay attention to what happens to the light bulb, and also what happens to the voltage over here. Because once I flip the switch over, then the battery is no longer able to give voltage to the capacitor, and it also can't give voltage to the light bulb. The only voltage given to the light bulb will be due to the capacitor. Let's see what happens. Whoa! If you noticed, the light bulb got dimmer, the capacitor's charge went down, and the voltage slowly discharged. Let's do that one more time. So the capacitor fills up, charges up with the battery, and as I discharge it, now the light bulb gets dimmer, and this voltage slowly goes down. Now I can change these values by simply changing the separation, which is at distance d, which changes the capacitance, or I can change the area, which also changes the capacitance. So let's just make a prediction. If the area and if the capacitance went way up, I wonder what's going to happen to this light bulb then. Whoa, interesting. The light bulb is much brighter than before, and it's also staying lit much longer. That's because this has a much better ability to hold on to charge and voltage, so it's going to discharge those at a much slower rate. So it's acting more and more like a battery. So the bigger you make the capacitor, the more it acts like a battery. So think about your little capacitors in your phone. They have very low capacitance, they're very, very, really small, which means it's going to happen really quick. And it'll slowly discharge, or quickly discharge, depending on the size.
Now as far as the equations go for capacitors, there are two equations for capacitors, And then there's a third one which we'll talk about when we talk about multiple capacitors. What happens if we have more than one capacitor? But two equations, just one capacitors. The first one is C equals Q over V. And the next one is C equals epsilon. We'll talk about that, times A over D. Now, C is capacitance. Capacitance is measured in farads. That's just a unit for capacitance. And really, in a nutshell, capacitance is just a measure of how good the capacitor is at doing its job. How good is the capacitor at holding on to charge? So the bigger the capacitance, the better it is at holding on to charges. So the Van de Graaff, for example, that I'm going to show you in a second here, is going to be a pretty good capacitor because it can hold on to a lot of charge. Whereas the little capacitors in your phone have a pretty small capacitance, like micro or millicapacitors, millifarads, right, or microfarads. Q is charge. So we talked about charge. It's just basically how much electricity is on the capacitor. So the bigger that is, the more electrons there are, the bigger the charge. V is voltage. That's essentially like electrical energy, but not quite electrical energy. It's actually energy divided by charge. But we talked about voltage already. It's measured in volts. Charge is measured in coulombs. And then that kind of ties in this first equation. The second equation, A is the area. So the more area that you have on the capacitor, the more charges you can put on the capacitor. So it makes sense they can hold more if there's a bigger capacitor. So that's the area. And then the little d is the distance away from the capacitor. It's the distance between plates. And what a plate is essentially is just a place for that capacitor to discharge. So if you have a capacitor here and some other thing that electricity can jump to over here, that distance is what we're talking about. Capacitors often use the word plates, where there's two metal pieces that are separated by a gap, or maybe some insulator in between, and they want to jump that insulation, that little gap, and that distance is what that value is given by. And finally, this epsilon is just a constant. It's called the permittivity of free space. It's a constant for all capacitors. It's a constant for electricity, essentially. And it's just given by this value. It's always 8.85 times 10 to the minus 12, and the units for it would be farads per meter. It's always that value. The only way you could change it is if you were to add some different type of insulation in this capacitor. It's going to change that value. Well, we're just going to stick with that constant value for all of our calculations. So there's the math behind it. Now let's start applying it and see what it looks like. So here we have a capacitor, and the charge is going to build up on the outside of this capacitor, and it wants to jump to a different location, like me. So as I turn this on, you start to hear that electricity build up. And so as I go in to touch it, all that built up energy from the electricity wants to go to something else, like me.
Static electricity.
Right? So, if I were to stand on here and touch this, ow, right? Now Alright. So, now, the electricity, I can feel it building up on me. It doesn't hurt because I've not reached ground, but the electricity is going to build up on me over time. My hair should start to fall off, or start to stand up. So you can see, as this electricity builds up, the person's hair is starting to stand up.
If you shake your head a little bit, it'll probably get a little more noticeable. And all I have to do to discharge that capacitor, you give my assistant here a high five, and all the electricity is going to jump to me, and then it's going to go away. Ready? 3, 2, 1, go! Ow! 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 All right, let's do some math. So, let's look at that capacitor, which when it built up charge, it built up a bunch of negative charges on the outside here. Those negative charges want to get discharged to ground. Alright, so what we can do is, if we know the capacitance of the capacitor, which I will say is 1 nanofarad, which is really small. Capacitance farads are very, very small values. I should say a farad is really a big value, so getting 1 farad would require a lot of charges. So this is the same thing as 1.0 times 10 to the minus 9th farads. That's what nanofarads is. That's the capacitance of this capacitor. The surface area of the capacitor is 1.5 square meters.
and it can hold up to 120 volts because it's hooked up to an outlet, which basically stores that charge built up in the outlet onto it for that voltage. How much charge can it hold, and how close can you get to the capacitor before it zaps you? What's the closest you can get before it actually will discharge? You're like, hey, those lectures are like, hey, I'm free. I want to get to that ground, that big finger over there. I want to get to there. How close can I actually get before I get zapped? So let's start with the first one. How much charge? Well, we have this equation that says C equals Q over V. Charge is given by the value of Q. So Q equals V times C. All right, so VC equals Q. If I get my handy dandy calculator, right? All I have to do is take my voltage, which is 120, and multiply by my capacitance, which is 1 times 10 to the minus 9th. When I do that, I get a value of 1.2 times 10 to the minus 7th, and that'd be coulombs.
That's pretty cool, Ohm. Alright, back to the math.
Now note that C is the units for charge and not the symbol for capacitance. They're both C, which is kind of confusing because C is a symbol for capacitance. It's also the symbol for coulombs, which is a unit. Now, how close can you get to it? That would be the lowercase d. How close can you actually get to that capacitor before it zaps you? All right, so here is the other equation for capacitance. It's this symbol times A over D, and we're looking for D. We want to solve for that D value. So we're going to multiply both sides by D, and then divide both sides by C, so we get D equals our constant times A over C. So remember that constant was 8.85 times 10 to the minus 12. The A is given as 1.5 square meters, and then C we just found C is given as 1.0 times 10 to the minus 9. All right, we're left with units of meters. So 8.85 times 10 to the minus 12 times 1.5 divided by 1 times 10 to the minus 9th equals 0.013 meters, which is a little over a centimeter away. So 1.3 centimeters away, that's how close I can get to this, which is about like that, before it zaps me. That's the absolute closest I can get. Now, doesn't mean that it can't discharge quicker than that because there's other factors that tie into it, but that's like the closest I can get before I get zapped. Very powerful. All right, closing thoughts here about capacitors. Now I lied. I said there's one more equation. There's actually 3 more equations, but they're not too bad. So let's talk about what happens if we have more than one capacitor. All right, one capacitor is great, but sometimes you need more. Sometimes it's useful to have multiple capacitors in a circuit. So let's say those capacitors are wired up like this. There's a battery here, and there's a capacitor, another capacitor, and they're right next to each other, but there's a gap between them. They're in series. World series. All right. So what you do to figure out the total capacitance in series is it's very similar to resistors. Think about resistors. When you had resistors in series, you just added them up. If you had resistors in parallel, then you had to do 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus whatever many of the R's there are. Then you just do that consistently. Now, mathematically, capacitors are exactly the opposite. When they're in series, then you do 1 over C series, the total amount of capacitance in the series is 1 over C1 plus 1 over C2. However, if they're in parallel like this, the same amount of voltage is going to go into this capacitor as this one, just like Kirchhoff's rules. Voltage in a loop is equal to the voltage of the battery. So this loop, if this is a 10 volt battery, this is going to have 10 volts, this is going to have 10 volts. And with this one, if this is 10 volts, this is going to be 5 and 5. All right, so the total voltage has to be used up in the loop, Kirchhoff's rules. All right, so you simply just add these up. So if this is a 1 farad capacitor and 1 farad capacitor, the total capacitance of this circuit will be 2 farads. Right? If this was a 1 farad capacitor and a 1 farad capacitor, I would do 1 over 1 plus 1 over 1, which is 2, and then that would equal
1 over C. So 1 over C equals 2, so C would actually be 1/2. So this total would be 1/2 of a farad, and this would be 2 farads. They're completely different. Even though both circuits are using 2 capacitors, they have completely different total capacitances. So this is one way to kind of increase or decrease your capacitance if you have set values of capacitors that you can use. Like maybe capacitors can only be a certain size because they have to fit within a component. They only have a certain capacitance, but you can adjust them by simply adding more. And more capacitors gives you more flexibility, gives you more storage as well. So lots of applications to using multiple capacitors. Now, charging and discharging a capacitor, there's an equation. And the equation is this. The voltage that you have, if you look back at this right here, if you notice, the light bulb got really bright and then really, really dim. It discharged. But it didn't discharge at a constant rate. The voltage, if you were to plot voltage over time, the voltage started really high at some peak voltage. That's V0. That's the peak voltage, the maximum voltage that it can reach, which would be the voltage of the battery, essentially. And then over time, it discharged like this. Now, this is not linear. It doesn't go down at a constant rate. It goes down at a very, very, very steep rate, and then it slows down. And that rate is a negative exponent. So it's E, the value of E, which is mathematical expression, E to the negative X. But in this case, your X is time, but it's affected by the resistance of the circuit and the capacitance of the capacitor. So the equation would be voltage equals your initial voltage times E to the negative this value of T over RC. Now we'll come back to do some practice with this later, but just note that capacitors don't charge at a constant rate. They discharge really quickly, and then there's going to be a couple electrons that kind of trickle off at the end. Even think about the Van de Graaff. When I touch the Van de Graaff, think about this. When I touch the Van de Graaff there, at first I got a big zap, but even after I got a big zap, there's still some remaining electrons on there. Like most of them got off, but there's still remaining electrons on there that are still kind of clinging on to that Van de Graaff. And so they slowly discharge rather than that quick burst of most of them getting off. You can see it much better here. This time my assistant, her hair is standing up, and when her hair is standing up, that's saying that there's charges built up on her, and those charges are repelling. And it kind of shows you that there's actually charges built up on her, so she's acting like a capacitor that's connected to the Van de Graaff. Now when I touched her, if you notice that some of her hair actually fell down, that's because some of those charges got discharged, but not all of them. Some of her hair was still staying up. And because some of her hair stood up, how I would discharge her even more farther is I would keep in contact with that object, the Van de Graaff, in this case her, and those charges would slowly dispel. But if you notice, at first, a quick burst, some of the electrons went away, her hair dropped, but not all of her hair dropped. So that's kind of a good indicator that she's acting like a capacitor. So hopefully that makes sense. Hopefully capacitors are ringing a bell and zapping your buttons. And thanks for watching this video, and look forward to doing some more circuit analysis with you. So take care.